Okay, so let's use what we know about solving second-order linear ODEs with constant coefficients to take a look at this application. So just a basic spring mass system. So a mass of 2 kilograms stretches an undamped spring by 196 centimeters. So we want to find the value of the spring constant K and include the correct units in MKS. So we want to find the frequency, the linear frequency of free oscillations on the spring mass system, and then the equation of motion. And then we'll find the first time that mass will pass through the equilibrium position. I guess since I don't have a lot of space, I'll try and partition off the space that I do have as best I can. So I have a mass of 2 kilograms, and I'm stretching an undamped spring by 196 centimeters. So the amount of stretch, I'll just go ahead and write in MKS units, will be 1.96 meters because there are 100 centimeters in every meter. So I just went ahead and did the conversion first. So first we wanted to find the value of the spring constant. So part A, well, in order to find the spring constant, if I hang a spring from the ceiling, it has a certain position on which the tip of it is. And if I attach a mass to it, it's going to stretch where that tip position is. So the spring has a spring constant K. The mass has mass we'll call M. And if we do a free body diagram on the mass, we should notice that the downward force of its weight should be perfectly counterbalanced if it just hangs there by the restoring force of the spring. Alright, and according to Hooke said that restoring force should equal to K times the displacement. Let's say that this displacement here, what we called S, or the amount of stretch in the spring. So we'll do K times S. Alright, since the mass is just hanging there. The weight, of course, is just the gravitational pull on the mass. And if we do a sum of the forces, we find that the sum of the forces in the downward x direction, if we assume that this is the positive x direction, we get W minus FR. And since it's a static system, W minus FR, of course, is 0, in which I can say mg for the weight, if I bring FR to the other side, is equal to K times S, in which K is equal to mg over S. And so we have 2 times G in the MKS system is 9.8 meters per second squared. In S, we have is 1.96 meters. This gives me a K value of 10 kilograms per second squared. Okay. At the top, I had a force, so that's a Newton, or a kilogram meter per second squared, divided by a displacement, which is measured in meters. So the kilogram meter per second squared over meter just leaves them with kilograms per second squared. Or I could leave it as a Newton per meter. Okay. So our K is 10 in part B. Whereas to find the frequency of free oscillations on a spring mass system. So our frequency, which is defined as omega over 2 pi. So it's our linear frequency is equal to our angular frequency over 2 pi. And by definition, our angular frequency we defined as the root of K over M, which I can now write as 1 over 2 pi. K is 10, M is 2. I get times root 10 over 2, which is 5. Okay? So my linear frequency is root 5 over 2 pi. Part C says find the equation of motion if the mass is released from rest. So from rest just says that the velocity at time t is equal to 0 is equal to 0. And it's released from a position that's 100 centimeters below equilibrium. So its initial position at time t is equal to 0. Again, we're in the MKS system, so it's going to be 1 meter. And since it's below equilibrium, and we define down as positive, and below the equilibrium position is positive, I write as a positive 1. Okay, so this really just helps flush out our initial conditions. All right, so let's go ahead and see if we can write down the equation of motion. So I'll write this as mx double dot plus kx is equal to 0 since we have a 0 forcing function. All right, and then I'll subject to this differential equation or governing equation to these two initial values. So let's go ahead and see if we can solve this. We have mx double dot plus kx equals 0, which I could write as x double dot plus k over mx equals 0. Right? Where the k over m, again, is my omega squared. So we already found omega as the root of 5. Our omega squared is 5, so 10 over 2, 5. And so we can write the solution. This is one of our special cases, or you can write the characteristic equation, and you'll see that this is case 3. But in any event, we'll get a solution of x of t equals c1 cosine of omega t root 5t plus c2 sine of omega t. Okay. And since I have a condition on the position function and on the velocity, I'll need to take the derivative of this function. Okay. If I take the derivative of this function, x of t, I'll get a negative root 5 c1 sine root 5t plus root 5 cosine root 5t times the c2. So now let me apply the condition that x of 0 is equal to 1. Okay. So if I go back to my x of t here, I get that 1 equals c1 times the cosine of 0, which is 1, plus c2 times the sine of 0, which is 0, and I'm just left with c1 equals 1. If I apply the second condition, which says that the velocity at time t equals 0 is 0, we get 0 equals, in this case, c2. Okay, because the sine of 0 return is 0, which will get rid of this entire first term. And then here I have the cosine of 0, which will give me a 1. I'll get 0 equals the square root of 5 c2, and c2 must be 0 since the square root of 5 isn't, of course. Therefore, my x of t is equal to c1, which is 1, cosine root 5t. And this is my equation of motion. Okay. In part D, I'm asked for the first time in which the mass is going to pass through equilibrium. Okay. Well, I know that the cosine passes through the equilibrium position at all odd multiples of pi over 2. And the first time the cosine passes through the equilibrium position is when t is equal to pi over 2 if I had the cosine of t. So without getting too involved in this, I could just set the argument root 5t equal to an odd multiple of pi over 2. Let's call this 2n plus 1 times pi over 2, where n is an integer. Well, it should be clear that the first positive time will occur when n is equal to 0, and then I'll have 0 plus 1 is 1 times pi over 2, in which I find t equal to pi over 2 radical 5.